morning. Let's conclude what we were discussing yesterday. Please tell them on the group that we started.
Some of these. And you ask me. Huh?
Please come just. Let me use your phone. You are using Android. If you are not sitting beside anyone. My phone is low. What about it? I don't want to use it to read out the question.
Oh, okay.
What's in your phone?
That's nice.
Applications of differential equations yesterday. We're going to continue with that today. So we'll just pick questions from the three different categories, then move on to the next one. Look at number 3 of yesterday's problems. Number 3. So we solved number 2 completely previously in the regular class. Also an example in your lecture materials. So I think if you didn't conclude it yesterday, you can conclude that from there. Look at number 3. The rate at which radioactive nuclei decay is proportional to the number of such nuclei that are present in a given sample. Half of the original number of radioactive nuclei have undergone disintegration in a period of 1,500 years. What percentage of the original radioactive nuclei will remain after 4,500 years? And 2, in how many years will only 1/10 of the original nuclei of the original number remain? So we want to find out firstly a rate equation for this decay. When we say something decays, that means that the mass reduces. Does that make sense to you? That tells you a reduction. So they say that the rate of decay is proportional to the number of such nuclei that are present. So let's say that we say let the number of nuclei present, let the number of nuclei present be x. So we now say that the disintegration of this altogether of the nuclei is proportional to the number. So the rate at which x reduces, is proportional to Are we together, please? The rate at which x reduces is proportional to x. That means that our x dt is proportional to x. Are we together? And if you are going to take care of this, to remove the constant of integration, constant of proportionality, you are going to have the x dt, so this is a constant of proportionality. So you can write the x dt is equal to kx. And you remember that? How to deal with proportionality, the direct proportion. So here, we're going to indicate the fact that it reduces. I mean, it's actually a decay. We can indicate that by putting a minus in front of this k. That means that we want to ensure that our k is always positive. We know that this rate should be negative at any time, and we expect that our k should always be positive. So to take care of that, we put a negative sign here just to indicate that this is a rate of decrease. Is that clear? It's not a rate of increase. Okay? Of course, if you did not put this minus sign, you are still fine. You still get the correct answer. Okay, just that you are going to be getting your k to be negative in that sense. Do you understand that? So anyhow you do it is still fine. But just to conform with conventions, that's why we are putting the minus sign to indicate that there is a decrease in the growth of this nuclei. Is that clear? Alright, there's a decrease. Okay, so let's move on now. It says that half of the original number of radioactive nuclei present have undergone disintegration in a period of 1,500 years. So let us solve this differential equation first. We know that k is a constant of proportionality, so we can solve this differential equation, okay, for x as a function of time. So you can easily separate the variables here and say that what you have there is just, when you separate this, that's going to be 1 over x. Does that make sense? The x is equal to minus k dt. Is that clear? Okay, so when you integrate both sides, k is a constant, so you can let go of it. I mean, just move it outside. And this is going to give you ln x is equal to minus kt, then plus some constant of proportionality c. Is that clear? Sorry, constant of integration c. And then from here, you can take the exponent of both sides. This is going to give you x is equal to e raised to the power minus kt multiplied by e raised to the power c. So from here, you can write that x is equal to, e raised to the power c is just c, and I write it as c e raised to the power minus kt. Does that make sense? Right, so the next thing is to actually find out the constant. And whenever you are dealing with something like this, you will usually make use of the initial value, okay, to get that constant. So what we can do here is to establish that, or say that let x naught be the amount present, that's the number of nuclei, at time t equals to 0, present at time t equals to 0. So if that is the case, we can use that to get this constant of proportionality. That means that we're going to have, by substitution, x naught to be equal to c, okay, e raised to the power minus k into 0. So from here, you're going to see that c is equal to x naught. So then it follows that our x is equal to c, which is x naught exponential minus kt. Does it make sense? Do you understand this idea? Do you understand this? And then another thing you can do is, from the information supplied here, you are told that you have 1,500 years. After 1,500 years, half the number of radioactive nuclei have undergone disintegration. That means that after 1,500 years, the x you have left is just x naught over 2. Does that make sense? Because half of the original amount has undergone disintegration, it means you have only half left. Is that clear? So that means that after 1,500 years, so we are saying that given that x is equal to x naught at t equal to 1,500 years. So in this case, our t has the unit of 1,500 years, so it has the unit of years, and that's fine. So if that is the case, we can substitute that so that we can get this constant of proportionality k. So when we make a substitution for that, I'm going to have this, x is not equal to x naught, x is equal to 1 over 2 x naught, because half of it has decayed at that time. Does that make sense? So that means that you're going to have 1 over 2 x naught to be equal to x naught e raised to the power minus k into 1,500. Does it make sense? Do you understand this? Alright. Usually we call this, listen please, we call this the half-life. Can you remember? When you did chemistry, we usually call this the half-life of the radioactive nuclei. Can you remember something like that? Half-life is the length of time it will take for half of the mass present to decay. Can you remember? Alright, so if I were to deal with that, just to avoid dealing with numbers directly first, I can call this lambda, based on our usual convention. We usually use lambda then. So let's say we have lambda here. What we want to get, of course, is to get our k, okay, the decay constant. Okay, if you want to get your k from this, x naught is going to cancel x naught. Is that clear? And then from here, you can simplify this just to remove this thing here. You're going to have this thing to be ln. When you take the ln of both sides, you're going to have this to be ln of 1/2. Does it make sense? It's equal to, this is going to give you what? That will be minus k alpha. Does it make sense? Lambda. And then from here, you can get your k. What will be our k now? K is going to be, ln of 1/2 is the same thing as writing ln of 2 raised to the power minus 1. Does that make sense? Do you understand what I just did? Alright. And this is equal to minus k lambda. I can write this as minus ln 2. Is it clear? When I move the power here to the coefficient, this is going to be minus k lambda. And of course, minus cancel this minus. So at the end of the day, you're going to see that k is equal to ln 2 over lambda. Does it make sense? Okay, or lambda is equal to ln 2 over k. Anyhow you want to say it. Alright, so is that clear? Is this clear? Is this familiar? Does this formula look familiar? Something you have done before in chemistry and possibly also physics. Okay, so that is that about our k. So we can just put that there, that our k is ln 2 over lambda. So whatever lambda is, half-life, our own half-life in this case is 1,500. So for our case here, our k is simply equal to ln 2 over 1,500. Alright, so you can leave it at that. So it will then follow that x is equal to x naught, okay, then exponential minus ln 2 over 1500 multiplied by t. Is that clear? So that will give us our expression for the amounts present at any time t. So if we want to get the amount present at any time t, I'm going to use that expression. So let us see. Let us try to answer the question we have been asked now. They said that what percentage of the original radioactive nuclei will remain after 4,500 years? The amount that will remain after 4,500 years. That means we want to get x altogether after 4,500 years. Is it clear? Okay, so what will be our x after 4,500 years? So we're now saying that at t equal to 4,500 years, we're going to have our x to what? X will be equal to x naught exponential minus ln 2 over 1500 multiplied by 4,500. Does that make sense? So 15 before 5, that's 3, Abby. That will be 3 ln 2. Does that make sense? So that means when we work further, this is going to be x is equal to x naught exponential. I can write this as this is minus 3 ln 2, Abby. So I can write it as ln 2 raised to the power minus 3. Does that make sense? Does it make sense? Okay, so I can now say that what I have here is going to be x is going to be equal to 2 raised to the power minus 3 of x naught. Is it clear? Because this e raised to the power this will cancel out, so this is going to be x is equal to 1/8 x naught. So that means you only have 1/8 of the original mass or the original quantity present. Altogether, after 4,500 years, you only have 1/8 of it left. Is it clear? Does it make sense? So try to think of it. If you are given this question in an OBJ test, listen now. And then you can remember your concept of half-life, okay, in physics or chemistry. You know, you can just solve it without doing all of these things. You can just, if this was what you were asked, for instance, you know that 4,500, if the half-life is 1,500, from what you already know now, half-life is 1,500. That means 4,500 years is 3 half-lives. Is that clear? After the first half-life, you're going to have only x naught over 2 left. Abi? Do you understand that? After the second half-life, you're going to have x naught over 4 left. And after the third half-life, you're going to have x naught over 8 left. Does it make sense to you? Do you understand what I just said? Okay. I mean that 4,500 is 3 half-lives. So, if you have x naught present before, after the first half-life, half of this will have gone. So you are going to have left x naught over 2. Does it make sense? After another half-life, half of this will have gone. You have half of this left. That's x naught over 4. Is that clear? After the third half-life, half of this will have gone. You are going to have half of this left, which is x naught over 8, which is what we just got now. Is that making sense? Does it make sense to you? Alright, so that's that about that. So let's move on to the next question here. It says that in how many years will only 1/10 of the original number remain? So how do you get that? That means you are given x to be 1 over 10 x naught. Abi? So that means you are asked to find out the time when x is 1 over 10 x naught. So we can do that together now. So this is the answer to this. And for number 2, we are now saying that when x is equal to x naught over 10, c is given by this expression. That means we are going to have this x will be x naught over 10. I hope you are following. Okay, and this is going to be equal to x naught exponential, using this formula, minus ln 2 over 1500 t. Okay, so we want to find t. It's obvious that this is going to cancel this, and then you can take the ln of both sides. I want to get that when you take the ln of both sides, you're going to have this thing to be ln of 1 over 10, that's ln of 10 to the power minus 1, equal to minus ln 2 over 1500 t. Does it make sense? Alright, then from here, you know, this is going to be minus ln 10 is equal to minus ln 2 over 1500 t. And then you can cancel this minus. And then from that, you can put together the coefficient. You can collect like 10. This is going to give you t equal to 1500 ln 10, okay, all over ln 2. That's log 10 to base 2 anyway. So you can get that with your calculator. What would that give you? So this will be in years, as expected. It will be in years. So 1500 ln 10 divided by ln 2. What's that from the calculator?
4982.
4982.
82.
4982. 4982.
49.
0.9. Alright, so that's 4983. 492.9 years. Does that make sense? That's reasonable, Abby. You find it reasonable? Because if x over 8, x naught over 8 remains at 4,500 years, and if x over 10 is going to remain, it should be longer than 4,500 years. Do you understand that? And it cannot be up to the next half-life multiple. Do you get what I just said now? It cannot be up to 6,000, because by 6,000 you should have just x naught over 16 left. Does it make sense? Okay, so that's that about that. So let's move on now. Let's talk about orthogonal projection. So write that if you haven't written it. So talk about orthogonal and oblique projections.
No slippers. We don't go yes. Yes, right.
Mas vou cuidar pra
What's it?
Tô clean.
So we talk about orthogonal and oblique trajectories. Orthogonal and oblique trajectories. So we say that, listen please, you are given a family of curves, you are a family of curves with similar equation. The only difference being the constants in that equation. Okay, when you change the values of the constants, we are going to get different members of the family of curves. So for instance, if you consider this equation, look at this. You consider the equation x squared plus y squared plus k or k squared equals to 0. Okay, we are going to get a family of circles, okay, with center at origin. You know that the equation of a circle with center at origin is x squared plus y squared equals to r squared. Have you? That means we expect that whenever you have something like this, you're going to have circles. Of course, this is going to be some, it's going to be minus k, so this is going to be some negative constants here. Okay, so that means that for different values of k, we are going to have different circles. Okay, so the radius will depend on the value of k. So this is what we mean by a family of curves. So for this, for instance, if I were to sketch this family, I would say that I have something like this there. I have circles here, concentric circles, so to speak. All have their center at the origin. So you're going to have circles like this, and so on and so forth. Okay, this is what we mean by family of curves in this case. So if you pick a particular value of constant k, you can have the radius to be here, and the radius will be here for another value of constant k. For another constant k, you are going to have this radius. So you can cover all possible radii by just changing the value of the constant k. Is that making sense? Alright, so that's what we mean by family of curves. So when we say that orthogonal trajectories, that means that we want to find another family of curves that are orthogonal to this family. That means that they will be at right angles to this family of curves. And I say, for instance, for this, when you say that a line or another curve is at right angle to one or another curve, we say that they are simply at right angles to their tangents. So if I draw a tangent to this circle, for instance, I draw a tangent to this circle at this point, you know what the tangent is? If I draw a tangent to this circle at this point, I can get a line that is perpendicular.
Maguna iko sawa.
You can get a line that is perpendicular to that circle.
Like you shake the.
You still recording?
Exactly. Like bad. Push it up.
Just hold it.
Hold it. Don't leave it up. Yellow, you don't need stretchers. Go buy one spoon.
So this is going to be perpendicular to this curve at this particular point. Perpendicular to a curve simply means it is perpendicular to its tangent at that point. Okay? So you can see that if I draw any tangent to any one of these, I can get a line perpendicular to it by just extending a line from the origin. So I see that I can get a family of curves that are perpendicular to this family of curves. Okay? So that's one of the applications of differential equation. Is that when I'm given an equation for a family of curves, I can get their gradients. I know that when two lines, you can remember when two lines are perpendicular, we know the relationship between their gradients. We say that the relationship between their gradients is such that the product of their gradients, m1, m2, is equal to -1. Can you remember that? When two lines are perpendicular, or two perpendicular slope of the tangent, the slopes of their tangent, M1 and M2 are related by the slopes of their tangent are related by M1, M2 is equal to minus 1. Can you remember that? That means that if I know the slope of one, I want to get the slope of the other, I'll just say M2 is equal to minus 1 over M1. Does it make sense? So that's what we're going to do here. If I have a family of curves and I want to get the orthogonal trajectories, I will get the slope of the family of curves and then use that to get the slope of the orthogonal trajectories. Are we together? So if I'm given a family of curves, I will differentiate such that I will get the y dx, okay, to be some function that carries x and y. Okay. When I have differentiated, this is going to be my m1. And for me to get my m2, that's our new dy dx. So I can call it dy dx prime. In this case, for the orthogonal family of curves, is going to be equal to minus 1 over whatever I've gotten here, f of x comma y. So I can now integrate this to get the equation for my orthogonal trajectories. So let's quickly solve some problems under this application. Look at number 7. Since you find the orthogonal trajectories of the family of curves x squared plus y squared equals c squared. That's for circles, x squared plus y squared equals c squared. Look at it, x squared plus y squared equals c squared. So we want to get the equation of the orthogonal trajectories of this family of curves. So what's the first thing we want to do? The first thing to do is to get our derivative, the y dx. We know the y dx will give us the gradient of the family of curves. Are we together? That means I'll first get the gradient of this family of curves. Just like in 100 level, usually you were taught, what do you call it now? You were taught coordinate geometry. In the coordinate geometry, if you are given a line and you want to get the equation of a line perpendicular to it, how do you do it? You first get the gradient of that line from its equation. When you get the gradient of the line, you need to get the gradient of the perpendicular line. Can you remember anything like that? Okay. So we're going to be doing something similar here. So the first thing to do here is to obtain the y dx. Of course, by implicit differentiation, we obtain the y dx. So our dy dx is going to give us expression for the gradient of this family of curves, or the gradient of their tangent. That's what I mean in that sense. Okay, so let's do that together. So we're going to get the y dx from this. What's that going to give us? It's going to be 2x plus 2y dy dx is equal to 0. Does it make sense? Then from here, we can make the y dx the subject. We're going to have the y dx is equal to minus 2x over 2y. Does it make sense? That means that the y dx is equal to minus x over y. Is that clear? Is this clear? Okay, so that means this is the gradient of, or this gives us the gradient of this family of curves. So if I want to get the gradient, so look at it now. This means that x, the gradient of the curves defined by the gradient of the curves defined by x squared plus